Today we're going to talk about the one big central equation that governs all of electricity, Ohm's law. And realize Ohm's law is to electricity what Newton's second law is to mechanics. It's the central idea around which absolutely everything else is based. So getting right down to business here, Ohm's law is given by V is equal to IR, where V is the voltage, or the electric potential. Remember, the voltage is really just the electric potential energy per unit charge. And the units of voltage are in fact volts, which are joules per coulomb. The I in Ohm's law is current. Really, that's the charge flow rate, or to put it more simply, it's the amount of charge that passes a point per second. And the units are coulombs per second. That's charge per second. But rather than referring to the current as coulombs per second, we refer to it as amps. And last, there's R, the resistance within a circuit. Now, typically you'll see this defined as the resistance of charge flow or the impedance of flow with a charge within a circuit or something like that. But the fact of the matter is really a resistor is simply slowing the charge flow due to the conversion of electrical energy to other forms of energy. And the units of resistance are what we call ohms, which we show with the Greek letter omega. But to actually understand how Ohm's law relates to this battery and this light bulb, we need to take a look at two seemingly different situations. In one situation, we're going to take a look at a dam holding back a bunch of water. And that water is going to be free to run through a pipe, which then runs over a water wheel, causing that water wheel to turn. And in the other situation, we're going to connect a battery to a light bulb with a wire that runs from one side of the battery to the bulb, then from the bulb to the other side of the battery. Now, looking at Ohm's law first, I want to talk about resistance. So starting with the dam, let's say that right here, there's a droplet of water. And that droplet of water has some gravitational potential energy. Now, when we let that drop flow through the pipe and over the wheel, that potential energy is going to turn into kinetic energy. And as the water wheel spins, it's the water wheel that's going to provide resistance to the flow of water, and in turn converting that water's gravitational potential energy into other forms of energy. Now, in a very similar way, the battery provides a charge with some electrical energy. And when that charge gets to a resistor, a light bulb, its electrical energy is going to be used up, or really the resistor is going to turn the electrical energy into other forms of energy, like light and heat. Now, if a single charge flows from the battery through the bulb, not a whole lot's going to happen. Just like if a single drop of water flows over this dam and around this water wheel, not a whole lot's going to happen there either. So in both cases, we need lots of flow. And once we allow a continuous flow of either charge or water, that's where we start to see voltage and current come into play. So let's talk about voltage. In the case of the dam, we could measure the amount of energy a liter of water could give to the water wheel. Now that energy would be measured in joules per liter or joules per gallon if you want to work in freedom units here. And we can see if we were to make the dam higher, then each liter or gallon of water would have more gravitational potential energy to contribute to the water wheel. And that's because the energy of the water possesses is really just mgh. It's gravitational potential energy. If we make h the height of the dam higher, then there's going to be more energy the water wheel can receive. The battery and bulb works almost the same way. The voltage is the amount of energy given to each coulomb of charge as it flows through this circuit. And if we increase the battery from, say, 1.5 volts, like a AA battery, to a 9-volt battery, then each coulomb of charge is going to be able to do more work on the light bulb, thus causing it to shine brighter. Now, last, let's talk about current. In our dam example, current is really, well, just the current in the water. That is how much water flows through this pipe or over the water each second. In a circuit, current's not too different. Only rather than measuring flow in something like liters of water per second, like we did with the dam here, we're going to measure the current in coulombs per second. And that's measured by looking at any point along the circuit and effectively counting how much charge passes a point in a second. Now we measure current in coulombs per second, which we refer to as amps. So it's Ohm's law that relates voltage, resistance, and current to one another. And anytime we have electrical flow, it's V equals IR that will explain just how much charge moves through a circuit and how much work is able to do on a resistor. For example, if we were to hook this battery up to a variable resistor, if we could increase the resistance of the resistor, that would mean the current would have to decrease. Or if we were to do something like change this 1.5 volt battery out for, say, a 9 volt battery, we would see that the current which passes through this light bulb would increase. So moving forward, you'll find that it's Ohm's law that's always governing what's happening in an electrical circuit. And on that note, that's all for now.